Our presentation today is brought to you by 2021 SURE program, sponsored by Chevron. Our topic is rheological fluid properties and applications. I'm Gabriel Kirk, and I'm Miguel Moore. Our faculty advisor was Dr. Kareem Salahpour from California State University, Bakersfield. And rheological fluids are smart materials that alter their apparent viscosity when subjected to an external stimulus. The two kinds of rheological fluids that we focused on for this presentation or for this project were electrical rheological fluids and magnetorheological fluids. Electrical rheological fluids, or ER fluids for short, consist of electrically active particles submerged in an insulating fluid that increase in viscosity when an electric field is applied. Magnetorheological fluids, or MR fluids, are composed of magnetic particles that are dispersed in a carrier and also experience an increased viscosity whenever a magnetic field is applied. So when ER fluids are exposed to an electric field, they increase in viscosity because the electrically active particles that are suspended in the insulating fluid bind together and form chains along the electric field. MR fluids experience a similar characteristic. When a magnetic field is applied, the fluid changes from a liquid to a more solid. The viscosity increases greatly because the magnetic particles suspended in the carrier oil become aligned along the magnetic field. You can see in that photo there in the corner how it forms chain-like structure, very similar to the ER fluid. So after becoming familiar with the theory behind these two kinds of fluids, our goal is to determine how much of the external stimulus is needed to experience the increase in viscosity, how quickly does this change in viscosity occur, and what are some of the possible applications of ER and MR fluids. To find out these characteristics, we have to design several tests. The ER test, the first one, is with L brackets with a plastic spacer that we electrically charge and submerge in a fluid. Our second test is with a tongue depressor, which we submerge in a fluid, then apply to statically charge a balloon. And with the MR fluid, we create a flow test with a plastic tube and funnel to apply magnetism to the fluid. And with the second MR fluid test, we had a test bottle filled with MR fluid with a bracket, and we pulled rubber bands and applied magnetism. The materials used in this are among this list. We're within our budget. The total cost was about $410, of which the MR fluid made up the most. So for our first test, we made the ER fluid using a concentration of about 50% cornstarch and 50% canola oil. We briefly submerged the container filled with the fluid in the L bracket design and noted the fluid's viscosity as it dripped down from the ends. We then generated an electric field by using a DC power supply that was connected to the ends of the L bracket and repeated the test from a range of 0 to 25 volts. After conducting the test with the varying amounts of applied voltage, there was unfortunately no noticeable change in the fluid's viscosity. Even when the power supply was set to the maximum of 25 volts, the electric field was too weak to notice an effect, and that's shown in these two clips. So that's no electric field applied, and this is with the maximum amount of electric field that we were able to generate. So for our second ER fluid test, using the same concentration of fluid, we briefly submerged the vertically mounted tongue depressor in the fluid and then placed a statically charged balloon nearby to see if the effect could be achieved this way. And so as you can see in this video, the viscosity of the ER fluid increased significantly when it was subjected to the electric field of the balloon. And so it's also shown that the fluid quickly decreased in viscosity as soon as the electric field was removed, showing that ER fluids work reversibly as well. For magnetorheological fluids, the first test was a flow test with a tube held by the stand, and fluid was poured down the funnel. Magnetism was applied to the fluid as it flowed down. We started with one magnet, then we did two magnets on each side. For the first test, there was one magnet, and
the fluid flows down and it thickens towards the center. As you can see here, it flows a lot slower. Without magnetism, the fluid flows straight down the tube, just like a liquid. But as you can see with the one magnet, it seems to solidify towards the center there, but it is still a liquid, just with a very increased viscosity. It's slowly creeping down the tube once it gets to that magnet. Still in a fluid state, but definitely a very increased viscosity. Right about here, you can see it dripping into the container at the bottom. For the second test, we did two magnets rather than one. You can see there that it's solidified where the magnets meet. We then remove magnetism to return it back to its fluid state. You can see they're solid right there. You remove them, and then it stops right at the other two magnets there. Basically a solid, not flowing at all, not moving at all. Very high viscosity. Then when we remove the magnets, it returns back to its fluid state. This was achieved with just two block ceramic magnets, the force of 4 pounds. For the second test, we did a test bottle full of the liquid, and we had a bracket in the bottle and attached rubber bands to the support stand. When it was a fluid, it should be just pulled straight in and out. When it is then applied magnetism, we'll pull it again to see if there's tension in the rubber band due to the increased viscosity. In this test, you can see that it slides in and out very easily without any tension as a fluid. There is no magnetism. Then when we apply magnetism, the viscosity increases greatly, and rubber bands then have tension. You see here, no tension without magnetism. It's completely liquid. We apply magnetism. It is now much higher viscosity. The rubber bands experience a lot more tension and force.
When it comes to ER fluids, we were able to conclude that they only increase in viscosity when a strong electric field is applied of at least 1 kilovolt per millimeter, making the use of these fluids less practical when compared to MR fluids. The concentration of electrically active particles in the carrier fluid also greatly affects the way it reacts to an electric field. ER fluids are easy to make because the materials are cheap and common, just like cornstarch and canola oil. They react quickly and reversibly to an electric field, and the effect can be limited whenever the particles settle over time and whenever the fluid is exposed to extreme temperatures.
MR fluids, we were able to get this effect with only a single bar magnet with full strength about 4 pounds, which is about 3,900 pounds. MR fluids are also more difficult to obtain compared to the AR fluids due to the intensive manufacturing process and just the cost and access. However, they do react quickly, reversibly to magnetic field, but this could be limited when the particles settle over time or extreme temperatures.
So now that we have a better understanding of how this fluid works, we were able to develop and demonstrate a couple of different applications. The first being this damper system using MR fluids. And so a damper is a device that reduces mechanical vibration, like a shock absorber on a car. So we place the lower half of our setup in the MR fluid, and we drop some weights on the top to see how the spring reacts. So that's how it reacts whenever no magnetic field is applied. And whenever there is a field applied, you can see that the spring absorbs the force a lot better.
So our second application we developed was a brake system with a spinning cap with MR fluid. This was a rotating cap, and then we'd have a fixed washer in the liquid. It's spinning freely as a fluid, but when we apply magnetism, it seizes up, stops the rotation as it solidifies. You can see here it actually holds on a spin. So the MR fluid works as a brake system on a rotating axis.
So the last application concept we developed was a clutch system using MR fluid as well. And so a clutch is a device that engages and disengages shafts in order to allow power to be transmitted from one shaft to another whenever it's needed. And so this video shows how the MR fluid was able to engage and disengage the top shaft when the magnetic field was used. So there you can see the clutch is engaged. And once the magnetic field was removed, the top shaft was disengaged and only the bottom one had power.
Other applications could include body armor, virtual reality systems like shoes or joysticks, prosthetic limbs, which you can see by the image here. Using MR fluid, they can make a prosthetic limb like a damper. Earthquake resistant structures, haptic devices like needle insertion catheters or to aid in surgery. Devices like that could benefit from MR and ER fluids.
So lastly, I'd like to thank Dr. Salapur, who is our faculty advisor, Dr. Andrea Medina, the CSUB Director of Grants and Outreach, and Chevron, who's the sponsor of this program. Thank you, guys.
Thank you guys for all your contributions and your help. These are different research we did to learn about MR and ER fluids and their applications. Thank you.